Well, I too would like to thank the organizers, the Institute, for a great visit. There's a, well, let me show you a picture which has everything. This is kind of, I guess, we want to compute potential flow over airfoils. Well, those are just cosine curves, but you get the idea. We're using conformal mapping, and all the information is basically on here. So you're given, whoops, you're given those guys, and you smooth out, successively smooth the corners with the Karman-Treff's map to get smooth curves here. And then one does the conformal map and methods we've developed, extending a method by Banks-Formberg for the simply connected case, which map from the circle domain to these smooth curves. It's a Newton-like method, so it needs a smooth boundary here. And we solve the potential flow problem in this circle domain. So in some sense, everything's done in this multiply connected circle domain, and everything's represented by Laurent series. Both the conformal map, and computing that is a nonlinear problem because you've got to find the boundary correspondences on each of these curves, and you've also got to find the centers and radii of the conformally equivalent circles. So they're more or less the conformal moduli. So all that's represented as a Laurent series with some extra terms, and then for the potential flow, we want the Cotta condition. So we want zero velocity at the trailing edge. So the potential flow is a linear problem. The simple thing I'm pointing out in this talk, and that's that the structure of the linear systems we get both for the linear problem and the interlinear systems for the Newton iteration all have basically identity or actually maybe more of a discrete Fourier transform matrix plus low rank and can be solved efficiently with a conjugate gradient-like method. So yeah, so there's an outline of what I want to do. I'll just show you the forms of the maps and the potentials. I'll a pretty simple example of what the main observation of what the linear equations look like, and then discuss a little bit. I'm not going to give you too many details here about the system for the complex velocity potential, and a few details, even basically fewer for the Formberg method, because that gets into some more details than I have time for. And then if there's leftover time, we've got a gallery of pictures of conformal maps. This will be posted. Some of these are by request. If you don't see one you like, fill out an order catalog and send it in. So that's the outline. Okay. So just, I will put it on have them posted on the website, and there'll be some references and so forth here if you want more information. So yeah, I always want to credit my longtime collaborators, Alan Elkrat and John Falsgraf, who we had a few decades of very satisfying work together. So all of this they would have been thrilled by these meetings we've had recently. And most of this is with some current or former PhD students. So the question really is, if you don't want to use rational function approximations, how far can you get with series, with Laurent series? I mean, there are limitations, and I want to kind of give you an indication of that. Okay. And by the way, the methods like Formberg's method and the extension we did to the annulus for the doubly connected case can use the FFT, so they're order n log n. N is the number of Fourier points in the boundaries of the circles. And we try to extend that structure to higher connectivity, only you lose the FFT, so you could basically do things in order n squared. Well, yeah. M is the connectivity and N is the number of Fourier points. So there's a little back, there's a reference to Fornberg's original paper. And as I say, this is it's old wine and new skins, in effect, because Ned Halsey did this sort of work back in the 70s at, I think it was at Lockheed, to actually design multi-element airfoils in the aircraft industry, but he used main contribution here is I've got some newer methods. My website, and oh yeah, the other inspiration was some years ago learning Nick Trefethen was emphasizing and Toby Driscoll using basically least square solutions with series to solve problems. So this is kind of a closer look at that in particular context. And there's some relevant papers, but that'll be on the website. Oh, another old thing I should, I didn't come across this paper by Prosnak, who I believe Bartek has told me he met one time in Poland, who did some of this work in the early 80s. I don't remember hearing about that until maybe the late 90s. And he used similar methods for a different conformal mapping method, but a somewhat similar solution to the velocity potential. One difference is he used the block Gauss-Seidel to solve the system. And then there's a nice survey by Rudolf Wegmann, who did basically everything we've done, only with Riemann-Hilbert problems for the linear inner systems. So, yeah. And what I can talk about here, I mean, as I say, there are limitations to all of this. And, the methods that map to the circle domain are usually more robust, more complicated geometries, and can handle corners. You've heard some talks by Nasser and Takashi Sakato with Amano's method and so forth. Then there's if anything, maybe this puts a little bit of Nick Trefethen's recent work using rational functions in some perspective here. And one could also argue, why not just solve the problem in the physical domain with integral equations, but well, that's certainly a viable option. And the other long-term, or well, goal I've been working on a bit with Chris Green is to connect all of these things up with the prime function. But that's work in progress here. So, all right. So here's the complex velocity potential for flow over M cylinders with constant velocity in infinity, circulation gamma. The CKs are the centers of the circle. RK is the radius. So we want the, I'll show you the actual linear system in a bit, but we want a linear system for the RKs and the circulations. And we'll really work with the complex velocity. So that is of our form, of a Laurent series form. And we'll get a nice system out of that. And then the conformal maps, what are they? Well, for the simply connected case, it's just the Laurent series. You want to get the boundary correspondences in such a way, you make a guess for the boundary correspondence, and then you force a correction which makes the negative index Fourier coefficients go to 0. Get a linear system out of that. That was Fornberg's idea, and we've generalized that well to the exterior case, to the annulus, and the one I'm going to be talking about here is the map from the multiply connected circle domain. So if I'm not stating all the theorems here, but if you fix the behavior at infinity and you're given the target boundary, then the circles are predetermined. And the job is to define both the boundary correspondences and the centers and radii of the circle. So that's a nonlinear problem, but the linear systems have the structure. Now, so here's the main observation. I've tried to make this a simple example I did with a student with a scalar Riemann-Hilbert problem in a multiply connected domain. So if you're, roughly speaking, if you're looking to find a Laurent series, and this is very roughly, we're solving problems that the real part of this thing plus some auxiliary conditions is equal to some right-hand side. So the idea was that to include the radii, that stabilizes things in a pretty obvious way once I show it to you. You don't include the radii, it's not so well conditioned. And what happens if you include the radii here? Let's see, you divide things up into block matrices involving the interactions of this is the interaction of the kth and the Knuth circle here. So those things, if k is not equal to nu, the entries fall off geometrically. But if k is equal to nu, you just get the DFT matrix, or a section of it. So that's very nice. And then the singular values of that piece, if they're normalized by 1 over root n, are it's just the identity matrix. So you end up, say for two circles, the diagonal blocks are nice DFT matrices, and the off-diagonal guys are the interactions, and the singular values of those guys decay rapidly. And this carries over when we look at the what should I say? Yeah, we take the real parts and divide the matrix up. And the other thing I didn't quite show you is there'll be extra conditions, basically m extra equations, just to solve for the m, for instance, for the m circulations. But that'll just be a rank m perturbation of this basic structure. So, whoops. So there's a simple example. There are two circles, I think 64 Fourier points, and one's the radius 1.3, the other's 0.4, and the singular values of that A matrix are, they come up a little bit here. They're on the bad logarithmic scale. There's a few small outliers at each end, but they're pretty well grouped. That's if you include the radii. Now, if you look at those singular values of those blocks, you can see the structure. The diagonal blocks are well conditioned, and the off-diagonal blocks are ill-conditioned. And just to illustrate, if we didn't include the radii, the singular values increase geometrically for the bigger circle and decrease geometrically for the smaller circle. So, and similar thing happens with the block matrices. All right, now I'm not going to tell you all the details about the linear systems. As I say, I keep pressing the wrong button here. We need boundary conditions for the potential flow, and those are that the circles should be streamlines. In other words, the imaginary part should be constant. What I use is that the derivative with respect to theta should be 0. And we set up of the imaginary part, and we set up a linear system from that. We want the flow to go to u at infinity, and then we have these m extra equations for the Cutter condition. And one can put that all, let's see, into, yeah, I'm not showing you the details, but just the structure of the matrix, then you divide up into real and imaginary parts of the Laurent coefficients. So those are vectors containing those real and imaginary parts of the coefficients, and the gammas are the real circulations. And that adds this border, rank m border. And then you can throw all that into conjugate gradient. Well, we use conjugate gradient for least squares. And because of that nice distribution of the eigenvalues, or the singular values, it converges superlinearly. And yeah, here's an example. So here's just, potential flow over 8 cylinders. Let's see. Here are the singular values. I guess I use 64 points on each times 8. What's that? About roughly a 512 by 512 system, or I guess plus 8. And this is the convergence of the conjugate gradient for least squares. You can kind of see where it steps down. There's about 8 of these steps until it achieves full accuracy here. And if you counted carefully the outliers, the singular values, that's just about the number of conjugate gradient steps. Another diagnostic tool is to look at the decay of the Laurent coefficients. So they're getting down to, where are we here, about, well, yeah, I guess that was a pretty easy problem. So about 10, or nearly the magnitude of the smallest Laurent coefficients on each circle is around near machine precision. Okay, so that was the linear potential theory problem. Now, going to be probably even more sketchy ultimately with the conformal map. So this was a method we developed several years ago. And what do we want? We're given the target regions here, and we want to compute both the correspondences of the boundaries and the centers and radii of the circles as part of the problem with the Newton-like method. And let's see, those dashed lines, just to give you an idea, those are the initial guesses. So you need a reasonable initial guess for these methods. So they're the initial guesses of the circles. And it converges almost quadratically, fairly fast convergence. And anyway, there's I more or less stated the problem, but so what do you want to do? You're given some parameterization, maybe analytic for those curves like ellipses or inverted ellipses is analytic parameterization, but often, how do you define a boundary curve? Well, maybe you just have a bunch of points, like a Naka airfoil. That's basically what they give, and you run a periodic cubic spline through. So you need some parameterization of the boundary, because the conformal mapping method has to make it a guess for the boundary correspondence, and then kind of move tangent until what? Until these things are the boundary values of an analytic function. Okay. So that's what I'm not, sorry. First we linearize around everything. Linearize to get a correction. This is at the Fourier points, at n Fourier points. The boundary correspondence and the centers and radii of the circles. We throw all that on the right-hand side, and then I say, I want to choose those updates in such a way that these guys are boundary values of a function that is analytic exterior to the circles. And keep pressing the wrong button. Yeah, and this will have to go to my paper for, but there's a relations among the Laurent coefficients, which can be turned into a linear system. And if you, it's a little bit of a long argument, but you can also finally say for m equal 2, you can put that in the block structure. Again, these diagonal blocks are nice. They're like identity plus compact and discretization, and the off-diagonal things are like discretization of compact, and the border stuff is what pulls in the extra parameters, namely the real and imaginary parts of the centers and the radii. All right, so all that goes through. Conjugate gradient works pretty well there. Okay, and then you do the Newton update. And just to Just put in here the Carmen-Treffs. So the final map, there it is. Yeah, I keep hitting the wrong button. So the final map, the Carmen-Treffs map, removes the corners successively, and then you do the Fornberg map, H, and compose that with the inverted Carmen-Treffs, and that's the final form of the map to the region. So there's another one. Okay. All right, so I've got a few more minutes, right? Do I? Oh, all right. This is what I wanted to do anyway. I was thinking it was the last day that maybe I shouldn't give too many technical details. I should just show pictures. so I put a 20 or so slides of conformal maps here, and I'll try and show some of the problems that come up with, well, what can be done with smooth boundaries. Corners are very difficult with combining corners with Fourier series. Even the smoothing corners, getting more than a couple digits accuracy is pretty difficult. And then there's another general problem which Nick talked about, the ill conditioning due to crowding. I'll show some pictures of that in both in the simply connected and the multiply connected case. All right, so here's the simply connected map from the unit disk to an inverted ellipse with a off. You can fix the center point and 1 point on the boundary. So and a diagnostic tool in this, if you don't really know the exact map to test it against, or you wouldn't be computing the problem necessarily. But if you watch the decay of the magnitude of the Taylor coefficients, that it looks like I got down, forgotten how many. I probably used, oh here, yeah. I guess I used 128 points here. Usually it's 2 to the m points. So it looks like I got down to about 10 to the minus 8 accuracy in this case. And you can start to see the distortions in the map here. There are two ways to ill condition the, say for the simply connected case, to ill condition a map. One is to pinch it, and the other is to stretch it. And the stretching is much worse. The stretching is like exponential in the aspect ratio, and pinching is more like algebraic. And in fact, if it's an analytic boundary, the map extends analytically beyond the unit disk out until it hits a singularity, and nearer those singularities, as Nick's calculation showed, the more difficult the map, or the more Fourier points or Taylor coefficients you have to take to get any accuracy. There's an exterior case, exterior of the disk to the exterior of an ellipse, which is just the Joukowsky map. So, yeah, I guess you can see here, most of the coefficients are 0. There's, what is it, z plus 1 over z. Well, alpha times 1 over z. So there are two non-zero guys there. Let's see, there's the annulus case. So this is a thin region, but there's really no crowding because you're mapping a thin region to a thin region. So, and it's a little hard to read, but I think we use the first half of the Fourier coefficients from the outer circle and the last half from the inner circle. So if you, it settles, looks like it settles down around 10 to the minus 5. And due to the symmetry, there are a lot of things that are about 0 here. Let's see. Oh, this is a little off center. One could, if one wanted, map, let's say, an annular region to an infinite channel with a hole in it. if you're not too worried. So plus and minus 1 go to plus and minus infinity. So if you're not too worried about what happens out near the end of the channel, that's probably pretty accurate in the interior. We did do Everett Croft, my master's student, extended this method to bounded case too. I wanted to put this illustration in because maybe it illustrates for the multiply connected case. What's a good domain? Well, what's a good grid? Here's one we generated from. We had maps. We could map circle domains to radial slit domains, and then invert that and map back basically the polar grid to this multiply connected circle domain, and then pull it over. So, how do you define a boundary? I wanted to say a bit about that. There's just a picture. We pick those circle points and run a periodic cubic spline, and usually I use this routine that uses the chordal arc length between the knots as a practical parameter that helps control overshoots. Let's see. There's a target domain. As I say, that's the map. That's actually a diamond. But I smoothed the corners out and did the Fourier map from here to here, and then restored the corners. But of course, they're not too well they are. The sides are straight, but the corners aren't well represented because it's the image of Fourier points. So there's some natural limitations there. Well, here's one. Somebody was asking about slits here. That's the map from the exterior domain. I smoothed out, I opened up the slit, I'll show you how in a bit, to smooth curve, and then did the Fourier map and inverted. And how did I do that? The slit took one point to 0, the other to infinity, and took a square root, and just had to be careful to stay on the right branch. The bottom of the slit had to go to one branch, and the blue, the top, to another. So that managed to work. I managed to get it to work for 3 slits too, as long as it wasn't too wavy. Ill conditioning due to crowding, we've heard a bit about that. So map from a disk to what is this? A 3 to 1, or I think this is a 1 to 5 ellipse with a 2 to the 10th Fourier points. You can see even the ends aren't very well represented, and there's an estimate we did that says, you can estimate the harmonic measure of that end patch in terms of the extremal distance from near the center to the patch, and that's roughly in the length of e to the minus pi times the aspect ratio of the domain. There's one where it elongated enough and it didn't work very well. So you'll see things like that. Now for the multiply connected case, what's crowding? Well, originally I thought the worst case scenario would be 2 parallel slits, and that brings the slits together. D is the spacing between the slits and R between the circles. And that's D goes like square root of R, but actually it's worse in the other direction with slits that are going to touch. In fact, it's in one sense it's exponential going from here to here, I guess. And those are gotten from Kober's dictionary. Here's a combined one, and well, I think a few other pictures here. Comments on future work. I'd like to add vortices, which I think is a big problem. I'd like to add the prime function. My aerospace engineers didn't laugh at me, and they may give me wind tunnel data to compare. And finally, I've been here since September, and I wanted to thank the Institute, Center for Math Sciences, the organizers, colleagues, for a great visit, and then that's potential flow. This is the limits of my artistic ability here over the CMS with no circulation because the time's about up. So, thanks. Put your map orders in at the desk there.